My name is William Loggy. Today I'd like to talk to you about the chemistry of the four-stroke engine. When you hear people talk a lot about cars, you'll hear a lot of words or terminology that don't necessarily sound like they make a lot of sense. Is it 1.8 liters? Is it a 2 liter? Did he get the V-twin? Is it a HODC? And to the layman, this sounds like a bunch of letters and numbers that have absolutely no meaning. And so today I'd like to bring a little bit of light to that and bring a little bit of understanding and meaning to what the hell all of that really means. By the end of this presentation, we are going to figure out how many liters of gasoline are used in a combustion reaction inside of the engine, how many liters of oxygen, what the ratio of oxygen to octane is, and finally we're going to figure out the real-world application for how many moles of CO2 and how much CO2 gas is produced from this reaction. So in 1876, Nicholas Otto invented the internal combustion engine, what we call the Otto cycle or the four-cycle engine. It's called thus because the engine rotates in two full rotations, causing four separate reactions, which draws in all the elements used to create the explosion side of our engine. It's used to power most of our modern vehicles, and the basic function of it is that fuel and oxygen are gathered into a central canister where they are ignited by spark, producing the fire and force that create the movement of your vehicle. So I'm going to write down the chemical equation of our reaction real quick. Octane is what we call a hydrocarbon, which means that it is created by having a series of hydrogen and carbon chains. If we were to look at this in Lewin's model, it's going to look something like this. With hydrogens in each one of our little outside breaks. Now, hydrocarbons are especially useful for combustion reactions because they are very flammable. If you take a hydrocarbon and you combust it, you will always end up with water and carbon dioxide, as well as a great deal of heat and energy produced. So our hydrocarbon here is going to combine with the existing oxygen within our cylinder. To yield or create a combustion reaction, 16 moles carbon dioxide and 18 moles of water. This is the basic chemical formula of what goes on inside of your car engine every time it operates. Let's pull over. Now we've got a lovely working model here for what goes on inside of the four-stroke engine. You'll see our first step, the piston head here draws down, holding in our fuel-air mixture, which is then compressed until it takes up roughly 1/12 the volume of space that it had previously occupied. Now, we talked about in our gas pressure laws that when you decrease the volume of a substance, you increase the amount of pressure that's being applied. So this increased pressure, already a heightened state, is then met with spark, turning both the objects in there into a temporary gas-vapor combination. In the laws of gas dynamics, we see in Charles' law that when the temperature increases, it shifts the volume. And as the volume shifts, it changes the pressure, according to Boyle's law. This means that the explosive reaction forces the piston down and creates the energy which drives our crankshaft in rotation. Finally, as that energy carries itself out, the engine opens up at the top, letting out the remainder of the gas, and then as the last energy runs out on the camshaft, it creates a vacuum force pulling in more fuel-oxygen mixture, which in full speed looks something like this. Now, we've talked about how the chemical reactions here create an internal reaction. but that doesn't necessarily translate to how it affects the external reaction, how it moves the car. According to the laws of Newtonian physics, an object at rest stays at rest unless acted by an outside force of equal or greater value. According to Newton's second law, the force applied to an object is equal to its mass times its acceleration. Well, when we were talking about gas constants and gas laws in this class, we talked about how the force applied is equal to the pressure in an environment divided by the area. So in the case of an engine, we have all the pressure of that reaction built up by the sudden shift in temperature is divided by the area, the surface area of the cylinder times the height of its depth, creates the amount of force that that car is being pushed with. So the more force we put, the bigger that explosion, the more force your car is given. This is where we get our acceleration. This is how a car speeds up. Now, this is important because when you hear about the size of an engine, you typically hear it in terms of liter or cc, cylinder class. These are measurements of the volume of the internal cylinder of the car engine itself, or the total volume of all the cylinders in a multi-cylinder engine. What this means is we can draw in more reactants and produce a bigger explosion, more oxygen, more water, more carbon dioxide. Additionally, when we're thinking of this in a purely chemical sense, we have the idea of what's called a theoretical yield. We've talked about theoretical yield in class. It's how much we expect to get out of a reaction. And in terms of cars, we think about this in terms of miles per gallon. When a car is being pushed, the force of that interaction, that explosion, is what's propelling it. So that force of the explosion directly translates into how far the car can be pushed. And it's being based on how much oxygen and fuel we put in. So miles per gallon is a literal translation of how much reactants we place into the car divided by how heavy we expect that car to be. This is why your fuel mileage can be changed by adding more people into the car or shifting how things are balanced. Now, before we go into the hard technical equation stuff, I actually have a video of a glass engine so you guys can see what this looks like in slow motion. Go play. There we go. You see the cylinder here drives up, met with an explosion, pushes out the gas and draws in new gas. Every time your engine turns over, this is the reaction that's going on inside. So you're literally rolling around with a large explosion of roughly 700 degrees Celsius right in front of you. All right. Now this is a chemistry class, so we're going to go on to the math side of things. That didn't work at all. There we go. So our first question is, given this chemical reaction and a density of fuel of 0.703 grams per milliliter, how many liters of octane are used in this combustion reaction? So to calculate this, we're going to use a little bit of our factors here. So we know that in this equation, there are 2 moles of C8H18. And the first thing we need to find out before we can use this density that we have is how many grams per mole octane is. So we would calculate out the weight of carbon. There's 8 of those at 12.01. There are 18 hydrogens at 1.008 each. And all of these in combination ends up being roughly 114.224 grams per mole of octane. Now that we've got our equation back down to grams, we can then apply it to our density. So, if it is 0.703 grams, we'll cancel off grams, so grams will be in our denominator. Per milliliter. In solving across, we cancel out our units. This is moles, cancels out moles, grams to grams. And finally, we arrive at 0.32496 liters, or 324.9 liters, roughly 325. And that is given an ideal state with, infinite volume in your engine. Obviously, this is an odd-shaped engine, and you'll see why in a moment. So this is how much octane we have in a single combustion reaction. We're going to put that number aside for later. Now, we're going to figure out how much, yes?
2 minutes.
Thank you, much better. I'm okay with verbals. All right. So now we want to figure out how much oxygen is involved in this reaction. Now, given Avogadro's gas constant, and assuming STP, we know that the 25 moles of oxygen will have a relative density of 22.4 liters per mole, making a total of 560 liters of oxygen. Now, I don't know about you guys, but I've never driven a car with a 560-liter engine. I'm pretty sure there are battleships that don't have it that large. But to figure out how this applies to us, we can add these together to figure out what our actual percentage by volume is inside of the engine. So if there's 560 liters of O2 and 0.32496 liters of octane, that's our total mass. Percentage of that is oxygen is 99.94%. Now the application of this is that when we hear the size of an engine, which usually you'll hear 2.3, 1.8, somewhere around there, we can create factors to figure out how many moles of reactant we have and how much actual fluid or gas will come out of this reaction. I'm going to demonstrate this by figuring out how many moles of CO2, and then I'll open the floor for any questions we may have. All right, so given a 2-liter engine, we want to find out how many moles of CO2 are produced by our reaction. We already know that that the percentage of octane would be the opposite of whatever the oxygen was. So in this case, 0.057%. Liters of oxygen out of the entire volume. So if we're going by percentages, we would assume 100. We would then multiply by whatever the molar value of octane is. So in our previous equation, we found that 2 moles equals this. So 1 mole of octane would be 1/2 that value. So 1 mole. Got that upside down. Cancel out liters. And finally, once we've gotten it back down to molar value, we multiply it by the stoichiometric ratio between octane and carbon dioxide, which is 2 to 6 or 1 to 8 if you want to reduce. That's really your prerogative. So when you multiply this across, what you end up with is, in a 2-liter engine, given that it's 99% oxygen and 0.00% of octane, we end up producing 0.057 moles of CO2. Do we have any questions at this time? All right, thank you very much. Have a great day.